A UW-Madison scientist is behind novel research to study tornadoes and storms.
I spent a lot of time just banging away at the computer.
Some scientists study severe weather after it happens on the ground. Lee Orff looks at them through a supercomputer.
I've found a way to bring these storms to life that other researchers haven't.
Computers allow him to build 10-meter resolution models that can directly simulate tornadoes.
I will do what I can to bring those storms to life so that scientists can see the intricate details of what happens when tornadoes form, and once they form, how they behave, and then how they decay.
We've had 22 tornadoes in the state of Wisconsin so far this year.
Yeah, this year has been a big year, I will say.
As we continue to trend toward record numbers of tornadoes and thunderstorms, he wants his work to keep communities safe.
The overarching goal of a lot of research like what I do is we understand the storm better so that we can predict it better, so that we can issue warnings for tornadoes before they occur and not issue false alarm.
Make sure to continue to check in with our First Warn Weather team for the latest updates. Reporting from UW-Madison's campus, I'm Catherine Merck, News 3 Now.
Tomorrow.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.